In this video, I'm going to go over section 8.2, which is titled more about confidence intervals. So this section was a lot more just conceptual than calculatory. And so there is one kind of calculation that happens within it, and it's a little confusing. So hopefully this will help clear that up. So in general, what we're looking at is if I'm given a situation, they want us to find what the appropriate interpretation of the confidence level is. So they give us a sentence frame in the lesson. So if we were to select many random samples of the same size from the same population and construct a C% confidence interval using each sample, about C% of the intervals would capture the parameter in context. So remember that we're whatever percent confident, right? So this number is C because they're saying it can be whatever your confidence level is. And so that's your confidence level. So that'll mean that C%, the same percent of the intervals will actually capture the parameter in context. And they give you a manipulation to show that how that works. So one thing to notice, it says like samples of the same size here, they're going to give you the sample size within a problem. So he uses this generator to talk about that confidence level. And so he picks a population proportion of 50%, a confidence level of 90%, a sample size of 30, and then he just picks 25 samples, right? And so these lengths are showing you what the confidence intervals were. So that dot is that middle point of the confidence interval. And then the lengths are the margin of error, which is the same because they're both 90% confidence level intervals. And so the true population proportion is that 50%. And so that blue line is showing you that if the interval touches that line, then it's captured it, right? And so the red one is the one that hasn't captured. So there was only one in that 25, which means it had a 96% rate of the intervals capturing the true population proportion. And then there was a bunch of them. They were like usually 92 or 96, whatever. I also captured one that he did that was 88. And so it's the same data. It's just that in these samples, 3 of them did not capture the true population proportion. And so 22 out of 25 is 88%. So it doesn't mean that each of these situations will capture the parameter in context of this population proportion in this example. It means that on average, as you do more and more and more and more, that average of those numbers will get closer and closer and closer to that 90% confidence interval. And so the rest of this talked about kind of optimizing confidence intervals and how the margin of error is related to different things. So changing the confidence level also changes the capture rate. So if I increase my confidence level, what happens is it increases the width of the confidence interval. So a 90% interval is shorter than a 95 is shorter than a 99. And so what that means is, so say that here is my true population proportion, right? So my P is there, and I'm looking at a 90% interval. The 90% interval would be smaller. So the idea is that if I have a smaller range of values, it's a little less likely that I actually got the true population proportion. But if I make it wider, I have more probability of getting that value. If I make it even wider than that, I have more probability of getting that value. So that doesn't mean that I am sure that I have it because I know what the value is, right? It's kind of counterintuitive to what you think. Like if I'm 99% sure, that means that I'm pretty sure what the number is. But in this case, it means that I've got a big enough window that it's very likely that the true proportions are within that window, okay? And then again, as I conduct more trials, each of these samples, if I average out the capture rate, that'll get closer and closer and closer to that confidence level. So if I do, 100 of these samples, 90% of those should, so 90 of those 100 should capture that population proportion. So when we construct a confidence interval, we want to have high confidence. And so this is counterintuitive because we want it to have a low margin of error, right? So we don't want to have a lot of room for error, and we want to know that we have the correct value. So remember that in order to have a lot of confidence, our interval needs to be wider. And in order to have a small margin of error, that makes the interval smaller, right? So the way that we can combat that counterintuitive nature is by increasing the sample size. So the bigger our sample size is, the more likely we are to have a small margin of error. And then the part that I think is most confusing is the idea of this like factorization of increasing sample sizes and what that is related to the margin of error. So remember that the margin of error is half the width of the interval, right? So if I have this interval, then this value, this distance here is the margin of error. And again, it's the same as this distance, right? Because it's right in the middle. So the margin of error decreases, which is what I want it to happen, right? It decreases as my confidence level increases. Right, so if I wrote something, decreases, sorry. So a 99% confidence level is going to have a larger margin of error than a 90% confidence level. It also decreases as the sample size increases. And this is the one that has a proportion that we can calculate. So they give the example in the problem that if I increase the sample size by a factor of 4, that will cut the margin of error in half, which is the width of my confidence interval. So what they're saying is, so say that I originally had a sample size of 10, right? And so if I multiply that by a factor of 4, means that my new sample size would be 40, right? And so what's going to happen with that is that that's going to cut my margin of error by a factor of 1 over the square root of that 4. Okay, so let's say that my margin of error was, I'm just going to use 1 because it's easier. So if my margin of error was 1, then this, by increasing my sample size by a factor of 4, is going to cut my margin of error in half, because 1 over the square root of 4 is 1/2. So this only works exactly when I have perfect squares that I'm multiplying by, right? So if I am increasing my sample size by a factor of 9, because 9 is the next perfect square after 4, then that's going to reduce my margin of error by 1/3. If I multiply by a factor of 16, 1/4. If I multiply by a factor of 25, 1/5. And so that's how that works that way. Another thing that we can look at is it might do it backwards. So if my margin of error sorry, not my margin of error. If my sample size is reduced instead, so say that my sample size was 100 and I changed that to 50 instead, right? So if I change my sample size to 50, then I'm really multiplying this by 1/2, right? So if I'm cutting my sample size, what's going to happen with my margin of error is kind of the opposite of what happened, right? So if I increase my sample size, my margin of error goes down. Notice we're decreasing our sample size, right? Our n is 1/2, or sorry, the value that we're factoring by is 1/2 now instead of 4. So it's a fraction instead of a whole number. So what would happen to my margin of error? I didn't change colors. Is, and again, we're using this formula, right? This is what happens with margin of error. My margin of error changes by 1 over a factor of the square root of 1/2. Okay, so if I calculate that, that actually ends up being the square root of 2, which is about like 1.41. Okay, so you can plug that in your calculator or think about it as this is 1 over radical 2. which is 1 times radical 2 over 1 is how I got the radical 2. And then just calculating, that's 1.41. So that's bigger than 1 times, right? But it's not doubling. So it's increasing my margin of error, but in the questions, it's going to use vague terminology because it doesn't expect you to calculate this. It wants you to understand that if I'm increasing my sample size, my margin of error is going to decrease. If I'm doing it by 4 or 9 or 16, some perfect square, it's going to cut 1 over the square root of that number for my margin of error. If I'm decreasing my sample size by a factor, it's going to increase my margin of error. Again, if I was cutting that into fourths, so if I cut it down to 25 instead of 50, that's when it would be doubling my margin of error. So it has to be a perfect square for us to calculate that. The last types of questions are asking you about how the margin of error provides this like variability or bias. And so pay attention to the last sentence of the question. If it says does not or does, that's going to indicate what your possible answers are. So it'll give you situations for studies, and then it will ask you either which of the following bias is accounted for by margin of error, something of that nature. If it says that it is accounted for from margin of error, your answer is always going to be random sampling. Okay, so because I'm conducting a random sample, I might not capture all of a true picture of the population, right? And so that variability is a factor in why I have a margin of error, why I don't know the true population proportion from one sample. If it says what the margin of error, what is not accounted for by margin of error, then you have 3 possible options. So you'll have these 4 options for every problem. Remember, if it says the word not, it's going to be one of these 3. If it doesn't say not, it's random sampling. So under coverage is when some members of the population are less likely to be chosen and cannot be chosen in the sample. So an example of that is like if someone's making phone calls based on a list of landlines, because not everybody has a landline, or if they're making those phone calls to landlines during like normal work day. So from 8 to 3, because that's when they're working, they're making those phone calls. Lots of people are not home at that time because they're also working from 8 to 3. So that would be under coverage. Non-response, when an individual chosen sample can't be contacted or refuses to participate. So something like an emailing out a question, or they just, if it's a phone call, they say, no, I'm not going to answer your question, but. And then response bias is when there's a systematic pattern of inaccurate answers to a survey question. So for example, when the person who has like is highly bought into the question. So for example, if like your professor asks you how many hours you studied, you're likely to not tell the truth because you know they want you to have studied for a while. And so that's response bias. So again, the only calculations are with that margin of error. The rest of this is all conceptual, fitting under those 2 categories.